Welcome to The Explainer. Today, we are staring down a mathematical beast, a ninth-degree equation that honestly looks impossible to solve. But what if I told you there's a hidden key, a secret pattern that can make this entire monster of an equation collapse into a single, simple number? Well, let's go find it.
All right, so here it is, our challenge, a ninth-degree polynomial with 10, count them, 10 different terms. Our only goal is to find the value of x that makes this whole thing equal 0. Yeah, just looking at it, the task feels, well, pretty huge.
So, where would you even begin? This isn't just some textbook problem you can grind through. This represents a whole class of equations that really push the absolute limits of what traditional algebra can solve directly.
To really appreciate just how elegant the solution is, we first have to understand why it's such a brute force problem in the first place. Let's take a look at why the usual methods just aren't going to cut it here. With a problem this complicated, you basically have two paths you can take. You could use a computer to get a really, really close estimate, but you're always going to have those tiny little rounding errors. Or you can find the symbolic solution, which is kind of the holy grail of algebra. We're talking a perfect, precise answer with zero guesswork. And that's exactly what we're hunting for today.
So, when your standard toolkit just can't get the job done, you've got to find a specialized instrument. And in our case, that new tool is a very specific theorem, one that's designed for exactly this kind of puzzle.
And the theorem makes a pretty bold claim. It's not about getting close to the answer. Nope. It's about finding the exact root for equations that most people would write off as impossible to solve with perfect precision.
So how in the world does it work? Well, think of our polynomial like a really complex lock. Most methods would just try to pick it or brute force it open. This theorem, though, it's different. It's like a unique key, one that was perfectly crafted to fit the tumblers and unlock the solution, almost effortlessly.
Okay, so let's pop the hood and see the engine that drives this thing. How exactly is this special key constructed?
Now, this formula looks incredibly complicated. I get it, but the real power is the idea behind it. It takes all the chaos from the original equation, all those messy terms and coefficients, and it feeds them into this very structured mechanical process. Don't worry, we're not going to calculate it by hand, but we are going to understand what this machine produces. You see, this isn't just a single calculation. It's a step-by-step engine. It takes the original coefficients from the polynomial, uses them to calculate a new base value, and then it kicks off this recursive loop. Each new result becomes the input for the very next step, creating this sort of chain reaction that just systematically simplifies the entire problem.
All right, theory time is officially over. Let's actually apply this recursive engine to our polynomial and watch what happens as we start to turn the tumblers on this lock.
So we feed the polynomial's original coefficients into the machine for step 1. And after all that complexity, something pretty remarkable happens. The first symbolic coefficient it spits out is exactly 0.
And this right here illustrates the power of this method, that 0 isn't an approximation, it's not a rounding error. The entire process is built from the ground up to produce precise, symbolic values at every single stage.
Okay, so what happens on the next step? We run the process again. And we get 0. A coincidence? Maybe. Let's do it again for the third step.
Still 0. A pattern is definitely starting to emerge here.
And in fact, as we continue this all the way through, all 9 steps, the pattern is, well, it's undeniable. Every single new symbolic coefficient, the very numbers that are supposed to rebuild the polynomial, they all simplify perfectly to 0. So, what does that mean? What's the consequence of all this incredible complexity, just repeatedly collapsing into nothing? It means the lock is about to spring wide open. It means that our intimidating 10-term polynomial, it was all just a disguise. The theorem has revealed its true, simple identity. All of those complex terms just collapse, and what we're left with is this core equation. X plus 1 to the 9th power equals 0. And for x plus 1 to the 9th power to equal 0, there is only one possible value for x, and it's -1. That's it. The entire complex structure, all 10 of those terms, was built around this single, simple integer. But wait, there's one final piece to this puzzle. A 9th-degree polynomial is supposed to have 9 roots. 9 answers, right? Well, the concept here is called root multiplicity.
And it means that -1 isn't just an answer, it's the only answer, repeated for all 9 of the equation's roots. You know, going from that monster polynomial all the way down to the number -1 is an absolutely incredible journey. But what's the bigger takeaway from this mathematical magic trick?
Well, what this really shows is a fundamental shift in approach. Sometimes the most complex problems aren't about brute force calculation. They're about finding the right key to reveal a hidden simplicity. This symbolic path proves that even for some equations that look unsolvable, a perfect answer might be hiding right there in plain sight.
And that leaves us with a pretty fascinating question to think about. What other problems out there, in science and engineering, maybe even in our daily lives, seem impossibly complex, but are really just waiting for the right key to unlock a surprisingly simple solution? Thanks for joining this explainer.